Welcome to our accelerometer design video. My name's Mona.
I'm Lily.
Alex.
And so basically the goal of this design was to learn about how angular motion translates into linear motion using the motors and gearboxes that we were given, and try and get up to 1G on the x-axis. So in our design brief, which was for the first part of this project, we included basically the mechanics of our design and tried to calculate how the angular motion will translate to linear, and Alex will talk about that now.
All right, so here is basically a little basic diagram of our design, and so we're going to have a rotational motion, and that's going to be at a constant angular velocity. And so basically, using the law of sines, you can come up with a relationship between these two angles. So you get sine of theta over L is equal to sine of phi over R. And so then by plugging in an equation for phi in terms of, or what you can do is you could take a phi or cosine of phi times L for this part of x, and then cosine of theta times r for that part of x, and if you add them up, you get x. And so then you can create the equation for x in terms of this, and then you also can use the first equation to substitute for phi in terms of theta and L. And so that's how you get this equation for x, and then using that, you can determine the acceleration by taking the second derivative. We don't show that here, but you get this long equation, and so then here you can find, we found the accelerations, we tried to get this equal to g, and so to do this we sort of determined values of r, omega, which is our angular velocity, and L, so that we could, so R, L, and omega, in order to get something that would give us peaks over plus or minus 1G. And so we had to, in doing that, we had to determine what was reasonable in our design, right? Like we couldn't use an L that was like a meter long. It had to be like a couple centimeters, and same with R and omega. The omega, we plugged in different gear ratios from the motor we were given. What else?
Yeah, so our actual design had a base made out of MDF, and we had a stand where we kept our motor, and then from that stand the motor was attached to the wheel right here, and then we had a slider attached over here and a little screw to keep the bar attached to the wheel. So basically when the wheel would spin, the slider would go along a track, and it was constrained on the top and bottom, so that way we could only get horizontal motion. So all of our base was made out of MDF, and then we chose acrylic for the what the slider was going on, as well as the actual slider and the wheel and the arm, just to minimize the friction, because in our calculations for our design brief we showed that the friction between MDF and MDF is much higher than it is from acrylic to acrylic.
So another important part of our design was being able to get the values from our accelerometer into values that are able to be read in terms of G. So we were given an accelerometer that you have to attach to part of our design in order to track the linear motion. So basically we ended up deciding to use Arduino, and the values from the Arduino gave it in the X, Y, and Z axis, but we just decided to attach it and track the motion along the Z axis, or the X axis. And basically from the input values, they go from a range from 0 to like 1023, so that had to be mapped based on the voltage and the acceleration that is proportional to that. So basically, we just mapped those voltages to units of G, and that's how we were able to test exactly how fast the acceleration was. And after we did that, it ended up being slightly slower
than we intended. So what we ended up doing is we originally optimized everything to have the gear ratio C, which was one of the slower ones, but once we did some initial testing, we weren't reaching the measurement we wanted for the acceleration. So that's most likely just due to friction along the slider as well as these interfaces. We could have gotten new batteries. There were a bunch of reasons why the acceleration may have not reached that, but we ended up bumping it up to gear ratio B, and once we did that, we were hitting the peaks of plus or minus 1G.
So that was the main difference between our design and what we included in our design brief and our actual design. Was mainly just switching the gear ratios. But other than that, the rest of our design pretty much stayed the same.
Yes.
Yeah, and we were pretty happy with the results. We ended up getting around 1G. It would fluctuate slightly to 2 or 0, but overall we were pretty content. I think in the future, to improve our design,
so after we ended up switching the gear ratio, the stand that the motor was placed on had holes that we could fasten it to, but once we switched around the gear ratio, the motor ended up being flipped, so we didn't exactly use those. So I think if we had more time, we could have recut it, just because taping the motor down was not the most secure option, but it still did the job. And then we also could have made the interfaces from the wheel and the slider a bit smoother, as well as where the slider was going back and forth, because friction could have caused it to not perform exactly as we intended.
Overall, I think our design was pretty good. It was pretty simple, so we didn't have too many factors that would go into why it might not have performed as how we wanted, but we didn't have too many moving parts, so it was pretty easy to test, see what we would want to fix, and then kind of change it from there.
Anything else?